This is a short tutorial on convolution primitives in HyperFun language. This is a list of supported HyperFun primitives and operations. Last time we discussed skeletal primitives, and this lecture is devoted to convolution objects. Let me remind the skeletal surface definition. As we can see, the summation of the individual scalar fields goes by skeletal points or other skeletal elements. If the number of skeletal points goes to infinity and the distance between them goes to 0, the algebraic sum turns into an integral by the definition. In convolution surfaces, the skeleton elements are not only points, but line segments, arcs, and other curves and surfaces. We can think of such a skeleton element as a set of points with the distances between them becoming infinitely small. In this case, an algebraic sum used in skeletal implicit surfaces turns into the shown integral of scalar field, or kernel, over the skeleton. Usually such integration means heavily numerical calculations. Convolution surfaces allow for different skeletal elements such as point, straight line segment, circular arc, and triangle. Any combination of these elements results in smooth surface without unwanted bulges, which is usually a problem of skeletal surfaces. Let's consider all these primitives in more detail. The first convolution primitive is skeletal point. Name function in HyperFun is HFConvPoint, where x are given point coordinates for the function evaluation. Vect is a linear array of skeletal points coordinates organized as follows. S is array of inverse kernel width parameters for each skeletal point. Smaller si means bigger i's component. T is threshold value for the entire model. Smaller t means entire expanded surface. Bigger T means entire contracted surface. This example illustrates the convolution primitive skeletal point, where smaller si's means bigger i's component. Next convolution primitive is skeletal line. Name of function in HyperFun is HFConvLine, where x are given point coordinates for the function evaluation. Begin is linear array of beginning points coordinates of line segments organized as follows. End is array of ending points coordinates of the line segments organized as follows. S is array of inverse kernel width parameters for each skeletal line segment. Smaller si's means bigger i's component. T is threshold value for the entire model. Smaller t means entire expanded surface, bigger T means entire contracted surface. This is convolution primitive example defined by 3 line segments. Next convolution primitive is skeletal curve. Name of primitive in HyperFun is HFConvCurve, where x are given point coordinates. Vect is linear array of skeletal curve points coordinates organized as follows. S is array of inverse kernel width parameters. T is threshold. Example of convolution surface with a skeleton curve defined by 5 points is shown in the image. Next convolution primitive is skeletal arc. Name of primitive in HyperFun is HFConvArc, where x are given point coordinates. Center is coordinate array for centers of arcs. Radius is array of arcs radii. Theta is array of arcs angles measured from the positive x-axis counterclockwise. 360 degrees are used for the full circle. Axis is array of vectors defining axis of rotation for each arc placed on local plane parallel to the xy plane. Angle are angles of rotation for arcs around axis of rotation. S array of inverse kernel width parameters. T is threshold. This is convolution primitive example defined by 2 skeletal arcs. Next convolution primitive is skeletal triangle. Name of primitive HFConvTriangle. X are given point coordinates. Vect is coordinate array for vertices of triangle. 9 elements for each triangle organized as follows. S is array of inverse kernel with parameters. T is threshold. Example of convolution surface with 4 skeletal triangles is shown on this slide. Finally, let's consider such convolution primitive as skeletal mesh. Name of primitive in HyperFun is HFConvMesh, where X are given point coordinates. Vertex is coordinate array for vertices of connected triangles, organized as follows. Index is list of vertex indices, 3 per triangle, organized as follows. S is array of inverse kernel with parameters. T is threshold.